Let's go ahead and now answer some questions about the scatterplot and residuals and line of best fit that we just did for the men's hot dog data, for the hot dog eating contest. Number 1, use the information from Desmos to write the equation for the line of best fit. So remember, we have that information right here with the slope and y-intercept. I'm going to round it to the hundredths place, so we have approximately y equals 1.24x plus 61.6. So the calculator calculated that for us. What is the meaning of the slope? All right, recall that we talked about this a number of times, that the slope is essentially the change in y for every 1x. So for every 1x, and in this case, x-axis represents years. So we have years are our x values. So for every 1 year, and then what's the slope? 1.24. 1.24 more hot dogs were eaten by contest winner. So the number of hot dogs increased by 1.24 per year. Actually, let me change my width of my pencil for the rest of these. For every 1 year, 1.24 more hot dogs were eaten by the contest winner. So it's increasing. So it increases by about 1 hot dog per year. .24, so 1 1/4 hot dogs approximately. All right, what is the meaning of the y-intercept? Okay, so recall that the y-intercept is this number here. And remember, this is years. So remember, that was 2010, because our year 1 was 2011, and year 2 was 2012, and so on and so forth. So in year 0, which was 2010, 61.6, or approximately 62 hot dogs were estimated to be eaten by winner. Remember, our line of best fit is really a prediction line. It's an estimated line using the scatter plot. So our estimation is at the beginning, in about 2010, there was about 61.6 or about 62 hot dogs were estimated to be eaten by the winner. We trace our pattern backwards. All right. Interpolation. According to the equation for the line of best fit, what would be the winning number of hot dogs in year 6? Okay, so remember, interpolation means that we're going to take an estimate that's kind of within the data set years. So within the years that we're kind of estimating here, this would be an interpolation estimate, all right, kind of within. And then we use the actual equation to make that prediction. All right, so let's take our equation, the y equals 1.24x plus 61.6, and we're talking about year 6. So let's do 1.24 times 6 plus 61.6. And at that point, you just punch that into your calculator. So 1.24 times 6 plus 61.6 turns out to be about 69.04. So 69.04, or about 69 hot dogs That would be the prediction according to the line of best fit, the estimated amount of hot dogs in year 6, remember, which was 2016, since we're going years from 2010. How does this compare to the actual value for the same year? Okay, well, let's go ahead and look at what is the actual for year 6. We'll go back up to our data, and we'll notice that the actual for year 6 right here was 70 hot dogs. Okay, so it's pretty close to what the prediction is, right? So the actual number of hot dogs was 70. And how does it compare? So when we talk about residuals, we do actual minus the estimated or the predicted. So actual minus estimated. Of course, you know the difference between 70 and 69. That is a very small difference, but let's just show that here. So the estimated was from the previous problem 69. So that is a difference of 1. So 1. So actual was 1 higher than the estimated or predicted. So pretty close. It's a pretty close estimate with our equation that we have for the line of best fit and doing an interpolation. Usually interpolation, you are going to get a pretty close prediction because it's within the data set of years. And so typically your prediction is going to be pretty close, a little bit higher confidence level. Okay, extrapolation. According to the equation for the line of best fit, what would be the winning number of hot dogs in year 22? Okay, so remember, extrapolation goes way beyond the data. So if we're extrapolating, that's going to go way beyond the measured extrapolation. Okay. Because you're talking about, okay, this was 2010, 2011, 2012, 2013, and so on, 14, all the way to 2022. All right, so year 2022. And what would this all extrapolate out to? So that's a good 12 years after the last data point. But let's see what it is going to predict at that point. So extrapolation, we use the same equation, 1.24x plus 61.6, but we're now going to put in year 22 and do that same calculation. Use our calculator for that. 1.24, let's try that again. 1.24 times 22 plus 61.6. It's about 88.8, so about 89 hot dogs. All right. Now, how confident are you with that? I don't know. 89 hot dogs? I guess that's about one more per year. So if people keep improving their competitive eating at the Nathan's Hot Dogs contest, then I suppose that could work out. In 2022, at this point when I'm recording it, it's 2021, so it would be 1 year from now. I wonder what the data would be. I don't know if they're having the hot dog contest this year. Sure they didn't last year with the pandemic. I kind of doubt they are this year, but who knows? What does the residual information tell you about your line of best fit? Okay, so the residuals, remember, are really going to tell us how close. So we look back at these residual numbers. They really tell us how close our data is to the prediction, how close the actual data is to the prediction. So if the numbers are big, that means it's not very close to the prediction. If the residuals are big, then that means that the prediction and the actuals are pretty far off. The closer they are, the better. That means we have a little bit more confidence. So let's write a little series of sentences to explain that here. So the residuals tell us how close the actual data values, in this case of hot dogs eaten, were to the estimated or predicted values. The closer the residual is to 0, the closer the prediction was to the actual values. So the closer the better. The closer to 0, the better. Now, looking at our data here, which ones were relatively close to 0? Well, I mean, this one's pretty close to 0. This one. I'm looking at like ones. Anything in the ones or less, I guess, in terms of distance. And then you've got some that are a little bit farther away from 0. So, I don't know. It's not the best. So about half were relatively close to 0. So in our data, about half were relatively close to 0. So the line was relatively close to the data. Close to the data. For the points. You know, wasn't great as I looked at this line. I mean, when we draw the line in there, it actually looks a little bit better than when we didn't have the line in there. But you know, it's relatively close. It's a decent prediction. It's not the best I've ever seen for how close the prediction is to the data points, but it looks fairly linear. And so I would say we have kind of medium confidence in that.